This presentation is entitled Humidification with Perma Pure. So Perma Pure humidifiers, as an introduction, are available to work in two methods. They're the water-to-gas modes and gas-to-gas modes. In the water-to-gas modes, you're using water that then saturates the Nafion membrane, and you can humidify a gas stream with the water from the saturated membrane. The other way is a gas-to-gas humidification, where you have a transfer of the water in the vapor phase. With either design or either method, our humidifiers have a scalable design with a wide range of performance achievable. There are no moving parts, and in case of the gas-to-gas version, there is no additional energy that is required to get the humidification to occur. So all of these humidifiers are all based on Nafion membrane technology. And Nafion is really the perfect material for water transfer. Nafion is a Teflon derivative copolymer that removes water or adds water via a first-order chemical reaction directly as water vapor. So in this diagram here, this is really designed to show removal of water from a gas stream where you're trying to analyze certain elements in the gas stream, but you can also humidify, and so you can actually look at it from the standpoint of the analytes there actually going into the membrane and seeing the water on the outside going from outside of the membrane to inside of the membrane. It works in the same way as drying. At any rate, the Nafion is a unique material. Let's just go over why the Nafion selectivity is so unique. So the Nafion permeation selectivity is based on chemical reactivity, not the size of the molecule. So it's not traditional permeation. So you can think of traditional permeation as kind of like a bug screen. You have a screen where you have holes of a certain size, and those size match up with the molecules you want to pass from one side of the membrane to the other. That's not how Nafion works. With Nafion, the water is actually becomes part of the chemical structure, and as a result, Nafion removes or moves water by a first-order chemical reaction so that equilibrium is reached very quickly. Only compounds that chemically associate with the sulfonic acid permeate through Nafion. Because this is a specific chemical reaction with water, the process is very selective. An interesting aside is that when you are humidifying with Nafion, it is truly only water that goes through. So any other chemical, including oxygen, that is in solution with the water is not going to transfer through the membrane. So as a copolymer of Teflon and sulfonic acid, Nafion is highly resistant to chemical attack, and the transfer of moisture is driven by the differential water vapor pressure between the membrane sides. That's for the gas-to-gas transfer. From the water-to-gas transfer, the water is just simply going to permeate and move through the membrane as a liquid. So let's look at water transfer in the vapor phase. Water or other polar chemicals can be transferred in the vapor phase. No energy is required. It's driven by the differential vapor pressure. No liquid water present to affect chemicals soluble in the water. It's highly selective and can be used to dry or humidify. In the liquid phase, it's a little different. Water or other polar chemicals can be transferred from the water phase on one side of the membrane to the vapor phase on the other. Remember that vaporization is endothermic, so unless the water is heated or the membrane is heated, the temperature will drop over time. Microscopic water droplets are present on the dry side of the tube, which could affect water-soluble gases. So if you want to humidify, let's say, a calibration gas stream of SO2, and as everyone knows, SO2 is highly water soluble, you probably wouldn't want to do that using water, using the water-to-gas method, because you will actually lose some of that SO2, because on the inside you will have microscopic water droplets. That's actually something we learned recently, because we had a customer that was trying to humidify just that, an SO2 calibration gas, and they found that they got different results when they did a gas-to-gas humidification versus the water to gas humidification, and we didn't know why. So the vaporization is selective. No other chemicals in solution with the water will pass through the membrane. So humidification of chambers where oxygen must be kept at a minimum would be a great application for our type of humidifier. So let's look at our products. Let's start with the BE series. This is a braided exchanger. This is braided Nafion tubing that is exposed to the atmosphere. The ultimate performance is a function of the dew point of the atmosphere where the unit is operating. It is often used to equalize humidity of a cal gas stream with the sample gas. It's available in a wide range of lengths and tubing diameters, with flow rates to 2 liters per minute and pressures to 255 psi in the tube when dry. So basically what this does is it equates the relative humidity, or the humidity in the gas stream that you're trying to humidify, that is the stream that you're putting through the center of the tube, with whatever is outside of the tube. So this is used very often when humidifying calibration gases, or also to humidify calibration gas to match the humidity of the sample gas that is being analyzed. So let's go to water to gas humidifiers. Liquid water is transported through the Nafion membrane and is vaporized or evaporated. It has the highest performance. That means from an efficiency standpoint, the water transfer rate is very, very high. We can achieve a high degree of humidity, up to 99% relative humidity. The water must be heated to restore energy used in evaporation, deionized, as ions in the water will reduce the performance by attracting themselves to the sulfonic acid chains on the membrane and thereby stopping the water transfer. And it must be circulated to maintain a consistent performance and a consistent temperature. The pressure drop may become a limiting factor, and water-soluble compounds may dissolve into liquid water droplets on the inside of the tube surface, like I mentioned before. And there is a pressure limitation of the tubing when saturated with water. Because Nafion tubing changes its mechanical properties when saturated with liquid water, it becomes very soft and kind of weak structurally. So the pressure rating drops depending on the thickness of the membrane. We drop the pressure rating to 15 psi for some and to 5 psi for our multi-tube humidifiers. That's differential pressure. Our most popular humidifier is the MH series single tube humidifier. This is a simple tube and shell design that functions with water, similar to how heat exchanger transfers heat. Basically, this is only for water to gas because one of the reasons Nafion is kind of tricky to work with, because when it's fully saturated with water, its physical dimensions increase by about 15%. So when we manufacture these, we actually cut the tube when it's wet so that it remains wet in the dryer, because, I mean, not the dryer, but in its housing, because if you dry it, it'll shrink, and it'll shrink out of the ends. If you took a regular standard dryer and you use that with water, it would expand too much and kink in the housing. So we have to create this humidifier with fully saturated Nafion. That's why it has to be kept wet, and it only works in the water to gas mode for that reason. The materials are in polypropylene, fluorocarbon, and stainless steel, with flow rates to 20 liters per minute and pressures to 15 psi 1 bar in the tube when wet. Like I mentioned before, these are water to gas only. They continuously humidify. They transfer only water vapor or water vapor into the gas stream. Fast response time, they're self-regulating, no moving parts, and have excellent corrosion resistance. I want to show you 2 ways that we have our customers use these humidifiers. This first version is humidifying with a liquid water reservoir. So we have the water mounted or kept in a reservoir at a location above the dryer, above the humidifier. so that the water is always dripping into the humidifier, and we heat the humidifier shell to the temperature at which we want the humidification to occur. That's how we also adjust the performance. The humidifier shell must be heated to maintain that consistent performance, otherwise the temperature will drop due to evaporation. So if you don't heat it, what happens is you have this temperature loop where it continuously cools as the water evaporates. The method that we recommend most strongly is humidifying with circulating water. This is very important because it's the only way that you can get a consistent performance out of this humidifier. You heat the water, you keep the water heated to a certain temperature, and you're constantly flowing it so that that continuously heated water is flowed through the humidifier, and that way you get a very consistent outlet humidity. Let's look at how our performance curves are generated and how to read them. So this is our typical MH110, which is a large diameter or the largest diameter humidifier that we have. And each of these curves show the humidification performance when using water at a certain temperature. So the actual end dew point that you want to achieve is going to be a function not only of your flow rate, but also of your water temperature. So you can actually improve the performance of your humidifier, change the performance of your humidifier by increasing the temperature. So for example, if you wanted a dew point of 40 degrees C, okay, and you wanted a flow rate of 5 liters a minute, so you would use water temperature of 70 degrees C with the 12-inch version. Now, if you wanted a dew point of 40 and you didn't have that high temperature of water, you can go to the blue curve where you can use water temperature of 50 degrees C and you'll get 40 degrees C, but you need to go really to the 48-inch version. So this is how you can kind of pick the humidifier you need, not only on the basis of flow and length, but also on the basis of what temperature you can heat the water to. Let's go to gas-to-gas humidifiers. Our large gas-to-gas humidifiers were originally designed for fuel cell applications, but can be used in many others. So we have a lot of people in the particle analysis field that use these to humidify particle streams. It's one of the common applications. Gas-to-gas is the most efficient method of humidification because no energy is required. It can achieve a high degree of water transfer. Over 85% of water content can be transferred through the membrane. No energy required, and is very highly reliable. So here is a example of humidifying with recycled exhaust gas from a fuel cell stack. Here you have your dry inlet going through the center and getting humidified, going through your fuel cell stack, and then coming out and being recycled back into the humidifier, doing its thing and humidifying the dry air inlet. The benefits of our humidifiers in this mode is that they have a very high efficiency, no power consumption, no freeze-thaw issues, and they're self-limiting humidification. So the humidification is dependent solely on the amount of Nafion present in the humidifier. So let's look at how we read a gas-to-gas performance curve. And this is actually confusing, so I want to take some extra time to explain this. We have two terms here, approach temperature and approach dew point. And what that means, that is the difference between the temperature or the dew point between what is being used to humidify, that is your source humidification stream, and your resultant humidification stream, your outlet stream. So for example, if I take a look at right in the center there, there's an FC 400-12 inch, and the center number there is 900 liters per minute. So at 900 liters per minute, okay, if I'm using an FC 400-12, my approach temperature is close to 4 degrees C. That means that if my inlet gas is 20 degrees C and my gas used for humidification is 50 degrees C, my resultant temperature is going to be 46 degrees C for an approach temperature of 4 degrees C. That is a difference between the two. And a similar way, this is how we look at the dew point. So if we use that same performance target at 900 liters per minute, we will see that our approach dew point is roughly 7.5 degrees. That means if our dew point of our inlet gas is 20 and the dew point of our gas being used to humidify is 40, that means our outlet dew point is going to be 32.5 degrees C for a difference of 7.5 degrees. So that's how we read these graphs. And here in a written form, I'll just go over these again, how to read the performance chart. The approach dew point is the difference in dew point between the recycled gas used for humidification in the fuel cell, this is the cathode exhaust inlet, and the resultant humidified outlet gas. The approach temperature is the difference in temperature between the recycled gas used for humidification and the resultant humidified outlet gas. And here is a calculation similar to the one that I mentioned on the couple of slides back. Here is an FC water to gas performance chart. You can use these for water to gas as well. And here you can see that the performance works the same way as our MH performance curve, where you pick the outlet dew point that you need, and depending on the water temperature that you are using, you will get the outlet dew point there on the curve. So let's just go over some of the basic humidifying applications that we find. Number one, sample gas conditioning to equate humidity, A/B testing with calibrated gas, gas conditioning to add humidity. There's a few manufacturing processes that call for adding humidity to various gases. Humidifying calibration gas for detection sensors that gives you higher accuracy when you're calibrating your gas detection sensors. Oxygen for breathing. So one of the big topics is now using Nafion to humidify oxygen streams for better comfort. For aerosol and particulate analysis, maintaining relative humidity for consistent measurements during the daily relative humidity cycle is an important application. Not only is Nafion used to dry, but it's also used to humidify in case of very dry sample streams. And it's also used for relative humidity experiments and maintaining baseline measurements, and also for fuel cells. We have what we call the Perma Pure 10 questions to select the right humidifier for your application. So to select the right dryer, we typically like to ask for extra information from you, a basic description of the application, whether you're familiar with how Nafion works or not. We want to know what your application challenge is and what you're trying to achieve, because many times the performance that we would recommend is in context of what you need. Of course, all of the parameters relating to incoming and outlet gas moisture content, target moisture level required, whether you're humidifying for water to gas or gas to gas, and what all the temperatures and other parameters and pressures of those are, and any other notes that can help us understand what you're trying to achieve. So when you come to us with a requirement, as much information that you can give us will only help us choose the right product in context. And that's the end of our presentation. I want to thank you for listening, and bye-bye.